Hello, my name is James Smith. I'm a machine learning PhD student at the Georgia Institute of Technology. I'm excited to present our group's work, Memory Efficient Semi-Supervised Continual Learning, The World is Its Own Replay Buffer, at the IJCNN 2021 conference. Our work falls under the continual learning paradigm. As visualized on the right, typical learning with neural networks involves offline training with shuffled data. By shuffle, I mean with respect to object classes over which we are expected to classify. That is, the distribution of object classes satisfy IID assumptions. In continual learning, tasks are instead encountered sequentially. Shown on the right, we see that classes appear in a single task and only in that task. We must train our model to perform well on all tasks up to and including the current task it is learning, without revisiting prior tasks. We encounter the catastrophic forgetting problem, where we perform bad on prior tasks. Specifically, we overwrite information learned on the prior tasks while learning the new task. Continual learning asks us, how do we acquire new information without forgetting? A classic way to mitigate forgetting in continual learning is through internal replay. As shown on the left, a continual learning agent has a data storage. As the agent moves to future tasks, it mixes in data from this data storage with the data from the new task. This approach, also known as rehearsal, works well for continual learning but requires a substantial memory budget. The more data you store, the closer you approach offline learning. Another approach, which does not involve storing data in the continual learning agent, is external replay. As seen on the left, the continual learning agent has access to an external data stream, such as streaming from the web. In this instance, there is no memory budget required by the continual learning agent. However, this approach does require having access to the external data stream. This may not be practical for use cases such as exploratory agents which do not have a strong internet signal. Besides, a constant internet stream is not free and requires additional hardware. Instead, we explore the setting where the continual learning agent has access to unlabeled examples in its own environment. As seen on the left, the agent does not store data for replay and is not accessing some type of external stream. Instead, it leverages unlabeled data from the environment for cheap replay. However, we cannot make assumptions on the distribution of the data under this scenario. The data will likely be correlated to the labeled task data in some way. This leads to our fundamental research question. How do realistic object-object correlations between labeled and unlabeled data affect replay in the continual learning setting? Formally, we introduce the realistic semi-supervised continual learning setting. In this setting, we have access to both labeled task data and plentiful unlabeled data from the environment. We represent this by using 20% of the data as labeled data. The labeled data in a given task follows a label superclass structure where object classes in the task are similar. We use the remaining 80% of the data as unlabeled data, and we explore different ways in which this unlabeled data may exist. For example, we explore no correlations, where no correlation between the labeled and unlabeled data is enforced, and we also explore several realistic correlations where object-object correlations between the labeled task data and unlabeled environment data do exist. We use a SciFar 100 dataset in our work because it is built on an existing superclass structure. The SciFar 100 dataset consists of 100 object classes. These 100 object classes can be separated into 20 parent classes, with 5 classes per parent class. This figure shows the parent classes for SciFar 100. For example, the flowers parent class consists of orchids, poppies, roses, sunflowers, and tulips. Furthermore, these 20 parent classes can be divided into 8 superclasses, with 2 to 5 parent classes per superclass. This structure, shown here, is nice for a semi-supervised continual learning setting. It allows us to divide up the tasks into the 20 parent classes and then use the superclasses to sample unlabeled data in each class, which is correlated to the labeled task data. This is an example of a task sequence with no correlations between the labeled and unlabeled data. This can be considered the vanilla semi-supervised continual learning scenario. Each of the 20 tasks consists of a CFAR 100 parent class. Thus, the classes in the tasks are similar to one another. For example, the flowers task consists of the 5 different flower classes. In this vanilla setting, we sample unlabeled data from all classes. We'll show in our results sections that we can train an agent in this setting to perform highly without storing any data for replay. This is an example of a task sequence with correlations between the labeled and unlabeled data. This is a challenging variant of semi-supervised continual learning because the unlabeled data only contains classes in the same superclass as the task. For example, task 1 is the flowers parent class. The labeled data consists of examples from the 5 flower types in the flowers parents class. The unlabeled data, however, consists of examples in the same superclass as flowers. Here you can see as the agent sees the 5 different flower classes as labeled data, it also sees fruits, vegetables, and trees in the unlabeled data stream. We will show in our results section that the existing continual learning approaches suffer in this setting, but our approach performs well. We design an approach which is directly motivated for our setting. Because prior task examples may exist in the unlabeled data, we want to identify these samples and assign them a pseudo-label to be used as a supplement or replacement to a memory budget of past task data examples. This involves leveraging out-of-distribution detection to identify the unlabeled examples that are in distribution. Since we are using pseudo-examples, we can combine this with the labeled examples for a class balance fine-tuning. This is typically done with samples from the current task data and past task examples. This is a crucial step in continual learning that's used to reduce task bias. We can also leverage the unlabeled data in addition to the labeled data for a knowledge distillation loss, which enforces similar predictions from past task solutions to avoid network forgetting. Finally, we want to leverage the unlabeled data for a semi-supervised loss, which will boost overall performance of our model. Using these intuitions motivated by our problem setting, we propose the Distill match method for realistic semi-supervised continual learning. Key to our approach is access to a large stream of unlabeled data. We use this unlabeled data and a frozen copy of our model from the end of the previous task for out-of-distribution detection. We assign pseudo-labels to the data selected to be in distribution. We then combine the pseudo-examples from the previous step with the labeled data from the current task. We use this data to calculate class balancing gradient weights and apply a class balance cross-entropy loss. This is equations 3, 6, and 7 from our main paper text. Second, we use both the labeled and all unlabeled data for local knowledge distillation. This loss is the KL divergence between class predictions from the past network and the current network. The idea is we want the current model to make similar predictions to our prior model over the set of past task classes. We found that out-of-distribution data can also be used for this loss, and therefore we use all unlabeled data in this step. This is equation 1 from our main paper text. Finally, we use weakly and strongly augmented versions of the unlabeled data for a semi-supervised consistency regularization loss. This loss enforces weakly and strongly augmented versions of the unlabeled data to be assigned a consistent class label. We found that out-of-distribution data can also be used for this loss, so we therefore use all unlabeled data in this step. This is equation 4 from our main paper text. We evaluate our approach in semi-supervised class incremental continual learning benchmarks using the CFAR 100 dataset. This is the less challenging setting where the unlabeled data is not correlated to the labeled data. Full details for our experiments can be found in the main text of our paper. We show that our method performs significantly high without storing any examples for replay. On the right, we show omega versus number of stored examples, our core set size, after training for 10 tasks. Omega is a metric for mitigating forgetting in which higher is better. We compare our method to several continual learning methods which are compatible with leveraging unlabeled data for replay. Base represents a neural network trained with Atom and is considered a lower bound. Because omega is a metric of average performance with respect to an upper bound, the upper bound in all of these experiments is 100%. E2E is end-to-end incremental learning, DR is distillation and retrospection, and GD is global distillation. Details on these methods can be found in our main text. Importantly, these methods are either designed or adapted for the semi-supervised continual learning setting and represent the state-of-the-art comparisons. In this plot, methods which require a course set are plotted by increasing course set size. Our method and global distillation, which require no course set, are plotted horizontally without a course set. We see that our method, Distill match, performs very highly with no course set at all. In fact, it takes roughly 750 stored images to match our performance, which stores no images. For perspective, this number is just under half of the number of labeled examples present in each task. The big takeaway from these results is that we do not need to store replay data in an environment in which the unlabeled data persists uniformly. We found that the realistic correlations increase the difficulty of the semi-supervised continual learning setting. Previous state-of-the-art methods, including global distillation, suffer in this setting. Because of the increased difficulty, we found that this setting requires a small core set of stored examples for replay. We showed that our approach, Distill match, performs best in this setting. We also show in our main text that our approach is robust to several realistic data correlations, including this one. On the right, we see that the previous state-of-the-art global distillation performs poorly in this setting. This is because global distillation assumes the unlabeled data to be entirely uncorrelated and uses this assumption for confidence calibration. Unlike global distillation, our method makes no such assumptions on the distribution of the unlabeled data, which is why we perform great under all settings we test. A big takeaway from these results is that we do need a small core set of replay data in an environment with correlated unlabeled data. We also show that our approach scales up to larger data sets. Here we show results for the Tiny-ImageNet dataset. Images have a larger 64 by 64 resolution, and there are 200 classes total with 20,000 labeled images and 80,000 unlabeled images. We evaluate in the no correlation settings because we are not aware of a superclass structure for the Tiny-ImageNet classes. On the right, we show that our method with a small core set performs best for this dataset as well. The takeaway from these results is that our method scales up to longer tasks and larger image sizes. In conclusion, our work proposes the realistic semi-supervised continual learning setting. Importantly, in our setting, object-object correlations between labeled and unlabeled sets are maintained through a label superclass structure. This is a realistic way to pose semi-supervised continual learning as a replay from an agent's environment. We showed that these correlations make our setting more challenging. State-of-the-art continual learning methods perform inconsistently in the SSCL setting. This motivates us to propose a novel method for the setting, Distill match, which leverages pseudo-examples, consistency regularization, out-of-distribution detection, and knowledge distillation. Our results show that Distill match is state-of-the-art across several realistic semi-supervised continual learning distributions. Thank you for listening to our talk. Check out the main text by following the QR code or visit the project URL beneath. I would like to acknowledge my co-authors, Jonathan and Yin Chang, for their work on this project. I would also like to acknowledge my advisor and project PI, Sil. Thank you again for watching.